Hey, hi everyone. Welcome back from the break. We are back for our last lesson of the webinar series, and we are going to be learning about how to do curve fitting with a library called SciPy. So Dr. McDonald is going to lead that session. So take it away, Dr. McDonald.
All right. Curve fitting is one of my favorite things. And I'm going to show you a little bit about curve fitting this evening. So I'm going to go back to my Jupyter Hub. And I think y'all are all probably already logged into your Jupyter Hub. So I don't think I need to go through the whole thing again. So basically, I have already started my Jupyter notebook. I've already started my Jupyter tool. Remember, this is kind of where you get when you first launch the thing. And I'm going to click into my MolSSI workshop folder. And at this point, we have a large number of things here. Now, if you were following along earlier and you remember how Dr. Nash a minute ago showed you how to upload a file, and then she's like, okay, now we have another one to do. If you did that, then you should have this file called datafitting.csv. And if you don't have this datafitting.csv file, I'm going to go through how to get that in there again real quick. All right, I'm going to put a link in the chat. And if you click on that link, it should just put you here in your browser. Okay. And you can see that this is actually a very small data file compared to the other data file that we did. We have X data, comma, Y data, and it's just 2 columns worth of data. So if you don't already have this file, then I would encourage you to go File, Save Page As, and then I'm going to put it in my Downloads folder, data_fitting.csv, and I'm going to hit Save. And then I'm going to click back over here to my MolSSI workshop folder. I'm going to hit the Upload button, and I'm going to find in my downloads, I'm going to find that datafitting.csv file. And some people say that the state of your file organization on your computer is equal to the state of your soul. And if that's true, then mine's a mess. But eventually, if I scroll through here, if I scroll through my mess enough and I find datafitting.csv, I can hit open, and then I'll see that right here, and I'll be able to click upload. And I already had it, so I'm going to overwrite it. But if you didn't have it, you won't see this message. And then in my MolSSI workshop folder, I should see datafitting.csv. Again, this datafitting.csv file in your MolSSI workshop folder. All right, once we have all done that and we have verified that we have our data fitting thing here, I'm going to come up here. I'm going to say new Python 3 notebook. And as I am wont to do, I'm going to make the top cell a markdown cell. And I'm going to make a title that says data fitting lesson. And then I'm just going to write a description. In this lesson, we will learn how to fit data to any functional form. And then if I hit Shift Enter, since that's just a markdown cell, it is going to just format my typing neatly. I want to mention here what I mean by any functional form, because I think most people have done data fitting at some level before. I know at my institution, we do data fitting even in Gen Chem. If you've made like a standard curve in a Gen Chem class and then you fit a straight line equation to that data, That is exactly what we're doing here today, except if you do your data fitting in a program like Excel or some other spreadsheet program, then usually there's only a couple different functional forms that you can fit your data to. Okay, so again, if you use a spreadsheet program to fit data, usually you can only fit your data to like a few pre-prescribed functional forms, like maybe a line or maybe a, second order polynomial or some basic stuff like that. But with the kind of curve fitting that we're going to learn in Pandas, you can fit your data to any functional form at all. And I love fitting data to different functional forms. So this is one of my favorite lessons. Okay, so we're going to use a bunch of different Python libraries in this lesson, all of which we have used before. So one of them is NumPy. So I'm going to import NumPy. And I don't know if Dr. Nash has shown you I know she's shown you that you can abbreviate the library names if you don't want to type in the full name. And NumPy is not a very long word, but lots of people still like to abbreviate it. So I'm going to import NumPy as NP. And then this is one that you did in your last week when we did plotting. I'm going to import matplotlib.pyplot as PLT. That's one that we all did last time. And then I'm also going to import pandas as PD, which we did in our prior lesson. All right. So then when I hit Shift Enter, you notice that this might take a minute to get all those libraries loaded in, but now we are good to go. So the first thing we're going to do is we're going to read in that file, that data_fitting.csv, and we're going to read it in exactly the way that we learned in our last lesson with a pandas data frame. So I'm just going to make a variable called df to stand for data frame, and then I'm going to do pd read_csv. This is just what we just did a minute ago. And then the file that I'm going to read in is data_fitting.csv. And then I'm going to hit Shift Enter, and it is going to read in that data. Now, you don't have to click over. You can stay here. I just noticed that I forgot to rename my notebook, and it's still called Untitled. So I'm going to take a quick pause and click on it and change this to data fitting. Just data fitting seems good. I'm going to do that quick change. Okay. You can stay here, but I'm going to click over and look at our data again. We can see that we had two columns of data that were labeled X data and Y data. So I'm going to pull in those two columns of data, and I'm going to say X data.
Wait, Dr. McDonald, can we see what's in it? What's in our df variable with the head function?
Sure. So that I would just say
df.head.
df.head. Oops. Man, I'm really struggling tonight. Okay, there we go. And there we go. We can see a few columns of our X data and our Y data. So I want to basically pull out this column of data. And in order to do that, I'm going to do it exactly the way that Dr. Nash just showed you. I'm going to say X data is equal to my data frame, and I want to pull out the X data column. And then I'm going to print it. And this is close to what I want for my X data, but it's not quite what I want. And in Pandas, whenever I pull out a column of my data frame, it always tells me the row label, which is in this case just the numbers, and then it tells me the actual data that I'm interested in. And I need to make a data structure that only contains the numbers. I don't want these row labels for my data fitting. So if I want it to not do that, then back up here in my X data line, I'm going to say X data equals data frame that I want the X data column. And then I'm going to put dot values, which means I only want the values. I don't want you to also tell me the row numbers. And now you can see I'll just get just that column of data pulled out. I'm going to do a similar thing with Y data. I'm going to go into the data frame. I'm going to tell it I want the Y data column, only the values, and then I'm going to print it just to make sure it looks good to me. So again, I'll just review what I did. I imported all these different libraries I was going to use: NumPy, matplotlib.pyplot, and pandas. I read in that CSV file, data_fitting.csv. I read that in to a data frame. And since I didn't really care what it was called, I just called it data frame. I checked out my data frame with head to make sure everything looked good. And then I wanted to pull out just these columns of data. So I did that particular column from the data frame and just the values, because I don't want it to show me those row labels. And another thing that's handy about doing this data read in with pandas is there wasn't very much data in this file, but if there had been a lot more data, I didn't have to count and I didn't have to figure out which column index this was. I could just give it the name and it would find the right column for me. And that's one of the real wins of pandas. All right. Okay. Now that I've got my data read in, the next thing I want to do is I want to look at this data, because I don't even really know what this data looks like. So I'm going to plot it. So I'm going to do plt.plot, and then I'm going to plot for my X values, X data, for my Y values, Y data. And then I'm going to plot this with circles, which is something that you learned about in our plotting lesson last week. And I'm going to hit Shift Enter. And this is what my graph is going to look like. So this is what my data looks like. Okay. So this, you don't know anything about the source of this data. This data would clearly not fit to a straight line. Like, that's certainly not a functional form that it would fit to. There are probably many different functional forms that we could fit this to. And looking at data and knowing what functional form it would fit to is actually very hard. So that's not really what we're going to talk about. I'm just going to tell you two functional forms that this data might fit to. And I'm actually going to make a markdown cell. I'm going to make a markdown cell and sort of type a little story to myself. So I'm just going to say what I just said. This data could probably be fit to many functional forms. Two functional forms. You might fit this data to are a Gaussian function or a cosine function. And then, just because I'm going to flex a little about how good at Markdown I am, I'm going to say, number one, Gaussian function. And then I'm going to actually typeset my equation real nice. So I'm going to put a $sign. And then the form of a Gaussian, if you have forgotten, is a y equals a e to the negative bx squared. And then once I'm done typing the equation, I put my other $sign. I kind of cap it off with the $signs. And then the other functional form I said is the cosine function. Again, I'm going to format this neatly just because I can. That would be y equals d times cosine of e times x. And then I close off my $sign. And then if I hit Shift Enter, you can see I've formatted my two functions really nicely. And it doesn't matter if you do this cell or not. I just kind of wanted to give you a little bonus about Markdown and remind you that you could type set equations really neatly, but you don't really have to have this cell at all. All I'm doing is just saying these are the two functions that I am going to fit my data to. And I might even only have time to do the Gaussian function. We'll see. Okay. All right. So let's talk about what we're doing here. So we have this set of data points, and these data points are our X and our Y values. You may remember that X is called the independent variable here, and Y is called the dependent variable because the values of Y depend on the values of X. And then what we want the computer to tell us is what are the best values for A and B for this particular set of data. If we want to describe this data with a Gaussian function, what are the values of A and B that fit this data? So that's kind of what most people mean when they are talking about data fitting. Okay? In order to do data fitting, we are going to introduce a new Python library. And we're going to be using a Python library called SciPy, which stands for Scientific Python. And SciPy is a huge Python library. It's one of the biggest Python libraries. So instead of importing all of SciPy, if I just did import SciPy, notice I'm not hitting enter here. If I just imported all of SciPy, this would take a really long time. So I'm not going to do that. I'm going to import just the one function that I need from SciPy. So I'm going to say from SciPy.optimize, I want to import just the curve fit function. So again, I could import all of SciPy, but I'm not because I don't want to waste my computer space. I'm just going to only import the curve fit function that I need. So then I'm going to hit Shift Enter. And you notice that even importing just that one function, it took a little bit longer than instantaneous. Okay. So if we are going to fit to a Gaussian function, the first thing we need to do is we need to define the function. And we already know how to do this from our functions lesson last class. So to define a function, we're going to say def. And then for the Gaussian function, I'm going to call it Gauss, G-A-U-S-S. And I'm going to start it with a capital G because the Gaussian function is named after a person, but none of that really matters, okay? And then when you're writing a function for curve fitting, this is how you always want to structure it. You want to have the independent variable, remember that's X for us, and then you want to have the parameters that you're going to fit, which in our case is A and B. Okay, so again, when you're specifying those inputs for your function, it's going to be your independent variable and then your parameters. Okay, then don't forget your colon. And now I'm just going to type in the function. I'm going to say y equals A. And then I have to remember how to do an exponential in NumPy. So that's going to be A times np.exp. That's the exponential function from NumPy. And then that's going to be -1 times b times x squared. And remember that to square something in NumPy is 2 stars. And then that's it. That's the only thing I wanted to calculate was y. So that's what I'm going to return is y. All right. And then I'm going to hit Shift Enter. And it's going to seem like nothing has happened, but now I have this Gauss function defined. Okay, so now I'm going to call the curve fit function that I imported from SciPy. I'm going to call the curve fit function, and the curve fit function outputs two things. Number one is the parameters, and the other thing that it outputs is the covariance matrix. And if you remember the covariance matrix from statistics, which I definitely do not, that is the covariance matrix we are talking about here. And the covariance matrix is what you use to calculate the standard error. And we're going to talk about that later. So if you don't remember what the covariance matrix is, that's actually not that important here. We just know that curve fit is going to output the covariance matrix. So we better have a variable there to hold it. Now I'm going to call curve fit. And all I have to pass in is the function that I want to fit, which is Gauss. Make sure if you spelled Gauss differently or you gave it a different name, you put your name. And then I put in the X data that I want to fit and the Y data that I want to fit. And I hit Shift Enter. And sometimes you get these runtime warnings, but that's okay. And I find that I get this a lot when I use exponentials. I don't know. It just has to do with your version of Python. So if you get this runtime warning, it's okay. And now it kind of looks like nothing has happened. But if we were to print the parameters, and we would spell parameters correctly, oh no, parameters is spelled correctly here, and I misspelled parameters up here. I'm going to go back and fix it up here. Okay, so I'm going to spell parameters right. I'm going to rerun that cell, and now I'm going to print parameters. And now you can see it's printed two numbers here. And this is basically the value of A and B that best makes the Gaussian function fit our data. And we could print the covariance matrix too if we wanted to, except since I barely remember what the covariance matrix is, that's probably not that amazing. Okay. Now, again, this value is the best fit for parameter A. Remember, this is parameter A right here. And this number is the best fit for parameter B for this particular data set. So I'm actually going to separate these just because I want to. I'm going to say the best fit for A is parameters element 0, because that was the first one, index 0. And my best fit for B is parameters 1, because it is index 1 in this list. And again, if I wanted to print them, I could do so. And the best fit for A is a number like 16.9, and the best fit for B is that number there. Okay? Now, as soon as I fit data, the thing that I always want to know is it a good fit or not? You know, does the Gaussian functional form fit this data well? So what I want to do is I want to basically go back up here, and I want to take all my X values, and I want to calculate what Y would be based on the Gaussian function with these two values of A and B. Okay, so again, what I'm doing is I'm taking all of my existing X values, and I'm going to calculate what the Y value would be if I used the Gaussian function with the values of A and B I just found. And then I'm going to plot those two things on the same graph and see how it looks. Okay, so I'm going to call these my fit values of Y. I'm going to call these fit Y. And to find them, I'm just going to call my Gaussian function, I'm going to use my X data from before, because remember I said I want to use the same X data, but then calculate what the Y data would be. And I want to use those fit A and fit B parameters that I just determined. Okay. And then if I look at this, this is going to calculate the values of Y based on the Gaussian function. That's what this is doing. It's using those best values for A and B, and it's calculating the Y's based on this function. Now, I'm going to make a plot, plt.plot, and I'm going to plot the data. So that's going to be X data and Y data. That's just my original data that I had before. And I'm going to plot it with circles, just like I did before. And I'm going to make a label indicating that this was the original data. And then I'm going to do another plot, plt.plot. And I'm going to plot the X data is the same, remember. But now I'm going to plot the fit Y data, the data that is based on my Gaussian function. And I'm going to plot this with a line so that it'll look different. And then my label for this is going to be fit, so that I can remember which one's the real data and which one is based on my fit equation. And then I want it to make a legend for me so I know which is which. So I'm going to do plt.legend so that it will show a legend on my graph. Okay. And now if I hit Shift Enter, the data is shown in the blue circles and the fit is shown in the orange line. And I feel like that looks pretty good. You know, I think that the Gaussian functional form with these values of A and B actually fits my data pretty well. I think it looks pretty good. Now, I can see that the fit is not perfect, okay? I can definitely see that the fit is not perfect. So that means that there's some standard error on my parameters. There's like a, plus or minus some error value because my parameters are not totally perfect. I'm going to write a markdown cell so I can make a note to myself.
Oh, Dr. McDonald, someone says their fit is not curved with the graph. Can you think of any reason why that might happen?
Probably. So my first question to them would be, do they have these same values that I have for their fit parameters? And if they do, then the problem is here with recalculating the values of Y. And usually it's because they didn't put in the fit values of A and B. They put in other values of A and B. But yeah, my first question would be, did you get these values? Did you get the fit values correct?
And Dr. McDonald, can you put a note in 16 about what you're doing?
Sure. So I would put, I am using the same values of X. I am recalculating my values of Y using the Gaussian function.
Right. And I have another comment about sort of what Dr. McDonald is doing here. So she's putting X data into the function, which is a NumPy array, and then calculating several values at once in one line, and without using a for loop. And that is because that is something that you can actually do with NumPy arrays sometimes. So we talked about doing that with Pandas data frames, how you can do calculations on several values at one time. You can do that with NumPy arrays also. So it's a little bit of a
bonus there. All right. So the other thing I wanted to show you Okay, so the other thing I wanted to show you is I can see that this fit is not perfect. Like, obviously, the line doesn't exactly follow all the points. And that's pretty normal when you do curve fitting. It's usually not like 100% totally perfect. So, so there is some error associated with this value of A and this value of B. So it's like 16.93, like plus or minus some, some number. And you can actually find that, and that's called the standard error. And you can actually find the standard error from the covariance matrix. And again, if you took a statistics class, you probably know a lot more about this. But what I know, I'm going to even make a little markdown cell to write myself a note. I'm going to say to calculate the standard error of the parameters from the covariance matrix, you take the square root of the diagonal elements of the matrix. You can do this with functions in NumPy. And again, I'm just writing this note to myself in a markdown cell because I'm not super great at statistics. So I have to remind myself that this is how you do it. Okay, so to find the standard error, the first thing we need to do is find the diagonal elements of the matrix, and then we need to take the square root of that. So to do that in NumPy, you say np dot diag, and then you feed in the covariance matrix. And you are careful to spell covariance correctly. And then you want to take the square root of this. So you can actually put this whole thing in parentheses and then say NumPy square root of NumPy diagonal elements of the covariance matrix. And you could do this in 2 lines. You could take the diagonal in one line and you could take the square root in the next line. But I always just do it in 1 line because I just remember that this is how you do it. And then I could print my standard error. There are, of course, 2 numbers here because this is the error for the A parameter and this is the error for the B parameter. And if I want to separate those things out, I can. The standard error of the A parameter is equal to standard error index 0. The standard error of the B parameter is equal to standard error index 1. I could do that if I want to. And then if I was like turning this into my teacher for my lab report, I might like write a really nice print statement. I might say, I might do like an F print statement. And I would say the value of A is, and then I would have it print the fit A value with a standard error of, and then I would have it print the standard error value. And then I might do another one of these for the B value. The value of B is, and then I would have it print the fit B value with a standard error of, and then I might have it print that standard error for B for me. All right. And then if I hit Shift Enter, It will print my sentences, except they will look ridiculous because I printed a gajillion decimal places. So I'm going to come back up here, and within my curly braces, I'm going to format this. So I'm going to say colon dot 5F to only print 5 decimal places on those values, colon dot 5F to only print 5 decimal places. I'm going to do the same thing down here, colon dot 5F, colon dot 5F. Oops, I missed my colon dot 5F. And now if I hit Shift Enter, it will make these 2 little sentences, and I can say the value of A is 16.9329 with a standard error. That's like a plus or minus 35658. Okay. I'm gonna give you 5 minutes to do the cosine function by yourself. And I'm just gonna tell you, I'm gonna warn you because I don't want you to lose confidence in your abilities. Okay. The cosine function is harder to fit. So if you do it and you do your plot and you've done everything right and the fit doesn't look good, don't panic. We'll talk about that in a minute, but I want everybody to spend 5 minutes and see if they can do the cosine function by themselves. And remember, the first step will be defining a function for the cosine function. And then you'll do the curve fit and then pull out your fit parameters and then see how good your fit is by calculating new values of y and making 2 new plots. Okay, so let's take 5 minutes. Oh, one other thing I want to tell you is if you are tempted to name your function COS, that is a reserved name in Python. So I would call it like cosine fun or something like that. Like, you know, don't just call it COS because that means something else in Python. Okay.
Dr. McDonald, I wonder if you can put a markdown cell with the form of the cosine function, sort of where we can see it here.
Yes. In fact, I can come back to my prior markdown cell and I can just copy it. And then I will make a new markdown cell and I will paste it.
Right, and just to be clear, what we want you to do here is to try to fit the data to a cosine function. So we just fit it to a Gaussian, and now we want to fit to cosine, which for cosine y equals d times cosine e times x.
All right, so let's talk through how I would approach fitting this to the cosine function. The first thing I would do is I would define the cosine function. So define cosine underscore fun. And then remember that the things that we always want for our inputs here are the independent variable and then the parameters, D and E. Don't forget your colon. Then we just type in the cosine function. So that's y equals d times, presumably cosine is a function in NumPy because everything is. Okay, so NumPy dot cosine of e times x. And remember, y is the only thing we cared about calculating, so that is what we are going to return. Then don't forget to hit Shift Enter. to make that function actually exist. And then we're going to use our curve fit function. We remember it is going to output two things, the parameters and our favorite friend, the covariance matrix. So then I'm just going to call curve fit. I'm going to pass it my function, cosine function. I'm going to give it my x data, and I'm going to give it my y data. Okay. Then I know that this is going to output a list of the two parameters. I'm going to go ahead and separate them. So I'm going to call my fit value of D parameters index 0, because that's going to be the first one in the list. And then my fit value of E is going to be parameters index 1. Then I'm going to find my new values of Y. So I'm going to call these my fit values of Y. And to find those, I'm just going to call cosine function. I'm going to give it the same x data that I did before, and the fit value of D and the fit value of E. And then remember, I'm going to put two graphs on one plot. So I'm going to do plt.plot. And the first thing I'm going to plot is just the data. So the x data and the y data. And I believe I've been plotting it with circles. And I'm going to make my label to say that this is just the regular data. And then I'm going to do another plot command, plt.plot. And I'm going to plot my x data with my fit y data. I'm going to plot that with a line so it'll look different. And I'm going to label this one fit. And then I think I've done everything perfect. I've done a great job. I hit Shift Enter. And look, the orange line doesn't match up with the blue dots at all. This is clearly a cosine function. It is kind of, bumping along here, but it doesn't fit. And this is really why I wanted to do this example, and why I, sort of pressed on in our last few minutes to do this, is because I wanted to talk about what should you do if your fit doesn't match your data points. Okay. And the answer is you should give curve fit a little bit of help. Okay. And what I mean by that is you should think about the cosine function, and you should give it a guess for what D and E are. Okay. So what I'm going to do is I'm going to copy this whole block that I just wrote, and I'm going to paste it down here because I want to do the same thing again. But this time, I'm going to create a new variable called guess. And I am going to guess at what I think the D and E parameters are. So let me scroll back up and look at my function here. Okay. I remember that the height of the cosine curve is what this D is. So if I look at my data, it looks like the height of this curve is something above 15. So I'm going to guess that the D value is 16. I don't have to be right. I just have to be closer. Then I remember that the E value in the cosine function controls how many bumps I have per cycle. So clearly I have way less than one bump. I haven't even made a complete cycle of my curve yet. So I'm going to guess that my value of B is something less than 1. I'm going to guess 0.1. Could I guess 0.5? Sure. I always try to guess kind of on order of magnitude. Do I think it's 1? Do I think it's 0.1? Or do I think it's 10? Just your best guess. Then in the next line where I am calling curve fit, at the end, I'm going to put in one more parameter. And I'm going to put P0, not P the letter O, P the number 0 equals my guesses. So I'm going to put P0 equals guess. And now, because I put all of this in one cell, it's going to rerun it. It's going to come up with new values of D and E. It's going to recalculate my fit values of Y, and it's going to remake my plot. And da-da, now it looks good. And now if I want to see how good my guesses were, I could print fit D. Remember, I guessed it was 16. Turns out it's 16.314. And I could print my fit E, and it was 0.1464. And I probably didn't have to guess super great in order to get it to work. I probably just had to get a little bit closer, and then the computer could find it. So that is how you introduce a guess if your curve fit does not look good. All right. And I could do the standard error, and I could do the things I did before, but I'm running out of time, so I think I will not. I'm going to scroll back up to let people see this. So again, this is exactly, everything is the same here, except I added this guess line, and then when I called curve fit, I put in that guess to curve fit. And that's what you should do if your fit is bad, is that you should make a guess. And a lot of times my students can only make one good guess. Like they guess that it's 16, but they can't figure out what the second guess should be. And if they can't figure out what the second guess should be, they often guess 1. And if that doesn't work out, then they guess 10. And if that doesn't work out, then they guess 0.1. It's a common strategy to just change your guesses until it works out. All right. So I do think we're almost out of time. Dr. Nash, did you have closing thoughts? This is our very last day of the workshop, so I feel like there should be more closing thoughts.
Yes. Thanks so much, everyone, for coming to all 4 sessions of this. We hope that you learned a lot during this workshop series, and the sort of last thing that we just did tonight with the curve fitting is sort of like the final thing where we brought a lot of these libraries that we learned together. So we saw how we used pandas, matplotlib, numpy, and then the new library SciPy, all like in this notebook to do something useful, which was curve fitting. We hope that you'll be able to use some of this stuff in your classes or sort of in your research or maybe in your career in the future. I think programming, it's pretty difficult to learn at first when you start programming, and it can be frustrating. But the more you program, the more you get used to it, and sort of the faster it comes to you. So if you're interested in continuing to programming to program or having a career in programming, then I would just advise you to practice. Just keep practicing. And we do have, other workshops that you can sign up for and continue learning. Actually, I have other things I want to add because I want to show them the MolSSI website. But Dr. McDonald, did you have anything to add?
No, not really. Just that I really enjoyed working with all of you, and feel free to connect on Twitter or LinkedIn if you want to keep in touch. And I will stop screen sharing because I know Dr. Nash wants to show you the MolSSI website and where you can find a lot more resources to continue your learning.
I think I've mentioned this site before, But you should be seeing the MolSSI education website, which the URL is education.molssi.org. And if you go there, you'll see something that looks like this. If you click on the resources tab, you'll see a list of programming resources come up. So actually all of the materials that we've been doing, they're available online. Most of them are under the Python data and scripting workshop. So I'm going to open that in a new tab. And then there's also one on data analysis using Python, and that's where the pandas lesson and the SciPy lesson are. So if you want to see, so I'll show you the SciPy lesson. If you need to go back and review any of that, these are online for you to read. And that is just something for you to know if you need to reference these materials again. So thanks, everybody.